Hello everyone, I hope you're keeping safe and healthy. We are going to now look at, for today's presentation, it will be on electric flux. So, we're going to define a few new concepts, a few new ideas. They may seem a little weird at first, it's kind of abstract, but there's a point to it all, and you'll see what it is. We're going to start by defining something we call the area vector. Okay, so an area vector is a vector that's associated with a surface. For example, for this blue square here, we're going to associate an area vector with it, and that helps us define certain properties of the area. The area vector, by definition, is perpendicular to the surface. So if I have a flat square like this, this is meant to be at an angle. It's pointing perpendicular to the surface, and its magnitude is equal to the area. So if this was like a 2 by 2 square, then the magnitude of this area would be 4, so the magnitude of this vector would be 4. Here's a couple other examples, right? The area vector is always perpendicular to the surface, and it has a magnitude proportional to the area. So this area vector here, the length of this area vector would be pi r squared for whatever the radius is for that particular one. By convention, if I have like a closed surface, in other words like a sphere or a cube or something, we'll pick the area vector to point outwards from the closed surface, because for any given area, like if you look at this one here, the area vector could point to the right, or you could choose it to point to the left, right? Let's do it with a, you could choose it to point to the left, but for a closed surface, we're going to choose it to be always pointing outwards. Now, we're going to use this area vector to measure how much electric field goes through a surface. So here's a surface, a square, right, with area A, and the area vector points perpendicular to it. And the electric flux is a measurement of how many electric field lines going through that surface. So if these red lines here represent an electric field, see how they're flat, uniform electric field lines? That means it's a uniform electric field that's pointing to the right. And we have a flat surface here. And the flux is E dot A. It's a measurement of how much electric field is going through this area. So the larger the flux is, the more electric field lines are going through that area, is the basic idea here. And here's you know, if this is the area here, then we'll choose, for this case, we'll choose the area vector pointing to the right, right? And so A dot E, or E dot A, is going to be E dot A times the cosine of the angle. And in this case, the electric field and the area vector are pointing in the same direction. So it'll be E times A, this is the flux, E times A times the cosine of 0 degrees, so it'll just be E times A. So that'll be like the maximum flux. That'll be the most flux. And you notice that as you turn it, let's say here, I were to turn it here, let's say this angle here was 30 degrees, then the flux through this one will be E times A times the cosine of 30 degrees. So this will be less than 1. So the flux gets smaller. And if you turn it all the way to here, the flux becomes E times A times the cosine of 60 degrees. Nope, not 60. Times the cosine of 90 degrees, which is 0. So here the flux is 0 in this case. Because if you look at the electric field lines, they're actually not going through the surface, right? They're just sort of skimming along the surface. They don't actually penetrate through the surface. So in this case, there's 0 electric field going through the area. Here there's a little bit, here there's more, and here's the most amount of flux you can have for that electric field. So as the area goes to 90 degrees, you get, when it gets to 0 degrees, you get 0 flux. Just to give you an example here, let's just make an example. So if this were 60 degrees, okay, then the electric field, let's say, it was 100 newtons per coulomb, and the area had an area of 10 square meters. Well, then the electric flux in this case would be E dot A, or magnitude of E times the magnitude of A times the cosine of the angle between them. So it'll be 100 newtons per coulomb times the area vector, which is 10 meters squared, times the cosine of 60 degrees. Okay, and the cosine of 60 degrees is an easy one, that's a half. So we end up with 100 times 10 times a half. So we end up with 500 newtons meters squared per coulomb. Okay, that's a straightforward example. So have a look at this one and think about it. The electric flux through this surface, is it going to be positive, 0, or negative? I'll give you a second to think about it. Remember, the flux is E a cosine of theta. So these are magnitudes, so these numbers are always positive, but this can be positive, negative, or 0. When is it positive? When is it negative? When is it 0? Well, in this case, it's positive because this angle here is less than 90 degrees. Anything between 0 and 90 is going to be a positive number. In this case, the angle between them, it's greater than 90 degrees, right? And the cosine of theta is going to be negative in that case. So in that case, we'll have negative flux. So when the area vector and the electric field are pointing roughly in the same direction, we get positive flux. And when they're pointing away from each other, we get negative flux. And when they're perpendicular, we have 0 flux. So that's just flux for the simplest situation where the electric field is constant and the area is flat. But if I have a curvy area like this, then the area vector at each single point is going to be different. It's pointing in a different direction. Like the area vector here is not pointing in the same direction as the area vector here. And so to generalize it, it would be the integral of an electric field over an area. So this is a surface integral. We're only going to argue through the simplest versions of this, but that's the basics. When we're doing it over, so this is how you would write a surface integral. You integrate E over the area of the surface that we're integrating. We'll see how easy that is. If it's a closed surface like a cube or a sphere, you put this little circle around the integral to indicate that it's the integral over a closed surface. So this is the general electric flux when everything is variable, and this is the easy electric flux for a constant electric field and a flat surface. So for example here, if E is 1800 newtons per coulomb and each side measures 0.32 millimeters, what is and the angle between them as shown in the diagram, there's 115 degrees. So what is the flux? So let's see. The electric field, let's just write down everything. So the electric field is 1800. I'll put in my sig figs at the end. The area is going to be 3.2 millimeters squared, right? So 0.0032 meters squared, which works out to about 1.024 times 10 to the minus 5 square meters. And we have our angle theta here, right, is 115 degrees. So let's calculate our flux. I'll sometimes put a little e here to represent the electric flux. So in this case, E times A times the cosine of the angle between them. Right? So E is 1800, A is 1.024 times 10 to the minus 5 times the cosine of 115 degrees. And what do I get? I get approximately here. I made a mistake. Times, there we go. I get minus 0.00779 newtons meters squared per coulomb. So that's the electric flux in this particular case. It's a very small area is why, right? The area here is teeny. In this case here, we're given the area vector as, we're given the area just in vector form and the electric field in vector form, so calculating the electric flux is even easier here if you're used to taking dot products. So it's going to be E dot A, right? So I'll write it out the long way, so it would be EX times AX plus EY times AY plus EZ times AZ. And so EX is, if you look, EX, it's right here. Oops. EX, apologize. EX is right here. It's minus 1 and AX is 1. So it's going to be minus 1, I'll put in the units at the end, times 1. EY if you look at the value in front of the y component of the electric field, it's 3. And AY is 2. EZ is minus 4. AZ is 0 because there's no z components to the electric field, or to the area vector. So we end up with minus 1 plus 6 plus 0, so we end up with minus 5 newtons meters squared per coulomb. How easy is that? A uniform electric field is given by that. There it is. It is 2I plus 2J, and I should give this some units, so let's give it units of newtons per coulomb. It says, what is the flux through the area? Well, there's two ways we can do this. Well, actually, there's one easy way to do this. So let's do this. Let's find the area vector for this square. You see the area on the right there? This is our area. So we're not given the vector, but we can figure out the vector. So I'm going to pick the vector. I'm going to pick it to be pointing this way. I could have picked the other direction, but let's choose this to be the area vector. What direction is that? Well, the area is in the xy plane, so the area vector is pointing in the k-hat direction, right? And we need the magnitude of the area. The magnitude of the area is going to be 2 meters times 3.5 meters, right? So it's going to be 7 meters squared. So 7 meters squared k-hat. So from looking at this picture, I was able to write down the area vector just by saying I need to know how strong the area is, and I need to know what direction it's pointing in. Then I take the dot product of the electric field and the area vector to get my flux. So once again, the electric flux is E dot A. Now you'll notice here that since the area vector only has a z component, right? If I take that times the x component, I get 0. If I get that times the y component, I'm going to get 0. So the only component that matters is the k component. So the electric field is just going to be EZ AZ. I can say that once again, the reason I'm taking this shortcut is that since this has no j and I components, when I multiply, that means the I component is 0, so I do 2 times 0. The j component for A is 0, so I do 2 times 0. But for the k component, I can do 1 times 7. So I end up with an electric flux of 7 newtons meters squared per coulomb. And please note the answer for the flux in every case is always, it's just a number, right? It's a measurement. It's not a vector. It's just a measurement of how much electric field goes through that area. All right, that's enough of that. So here's a couple of practice problems for you to try on your own. I may assign this as an online activity, so make a note. This is the fun one. And I'll add a little elephant to remind you that it's fun. Okay? Now, we're going to talk about electric flux through closed surfaces now. So for example, if I do electric flux through this cube, and I'm going to draw an electric field line. So here's my electric field line, like this. And here's another electric field line. Each electric field line that goes into the cube also comes out of it. Same here. All the electric field lines go through the cube. So if I were to change the surfaces, if all the lines coming in also come out of that cube, the total flux of that surface will be the same in most cases. We'll see a little bit more about why that matters later on. So here is a cube, and I'm calculating the electric flux. So imagine this is one electric field line coming through this cube. And the electric field line's coming along, and when it hits this surface, there's the area vector. It's pointing perpendicular to the surface. So electric field's going that way, area's pointing that way. The angle between the two of them is greater than 90 degrees, right? This is greater than 90 degrees, so it will be negative flux as the electric field line goes in. And over here, as it exits on the other side, it's less than 90 degrees. So in that case, the flux will be greater than 0. So when you have electric field lines that come in and exit, basically on average, they're going to cancel each other out. We have the flux going in and the flux coming out, and they're going to sort of cancel each other out. So imagine inside this surface, this cube surface, and remember these area surfaces that we're calculating for, they're sort of imaginary surfaces. They're not real things. They're just helping us understand what's going on. So let's say I have this cubic surface, and I have a positive charge plus Q inside of it. So what are the electric field lines doing? Well, all the electric field lines are leaving the positive charge and they're going outwards. They're all going like that. And so you notice that the flux in each case is going to be greater than 0. The flux there is going to be greater than 0. The flux there is going to be greater than 0 here. If that's my area vector and that's my electric field, the flux here is also going to be greater than 0. So the flux through each of these sides of the cube is going to be greater than 0. Any field that starts inside the surface will have a net positive effect on the electric flux. So in other words, the electric flux inside the whole thing is going to be positive because every field line that goes through this is coming out of the surface, and it's always going to be making an angle of less than 90 degrees with the surface. And so you're going to get positive flux. So if I have positive charge inside my cube, I get positive flux. And the opposite is true if it's negative, right? If you look here, if I have negative charge, remember all the electric field lines for negative charge point into it, like so. And so here's, oh, that's not it. Here's the angle between the area vector and the electric field. And you see that that's greater than 90 degrees. And so we're going to get a net negative flux. So the interesting thing is, when I look at the total flux through a cube, or through a surface, it will be negative if there's negative charge inside of it, because there's all these electric field lines going into the cube, and the area vector is pointing out of the cube. And if I have positive charge inside my surface, then the total flux is going to be greater than 0, because the electric field lines are all going away from the positive charge and they're all going to be pointing outwards. Let's say I have a charge over to the left outside the cube. Well, you notice that each line that comes in also comes out. All the lines that come in also come out. So the total flux through this cube, even though this surface will be negative and this surface will be positive, the total flux is going to be 0. So it turns out that the total flux through a cube, electric flux through a cube, depends on whether or not there's any charge in it. It's kind of handy. So once again, electric flux is, in general, an integral of an electric field over a whole surface. And these surfaces that we measure the flux through, we call them Gaussian surfaces, for reasons that you'll see soon enough. So for example, what is the flux on the left face of this cube? Is it plus E times L squared plus E times L, 0 minus E times L, or minus E times L squared? Pause and think about it. Well, it turns out it's going to be minus EL squared, because it's, remember, the flux is equal to E, oops, that's not an E, E times the area times the cosine of the angle between them. In this case, it's the E, and the area is the area for the left side of this cube. It's going to, if it has length L, the area is L squared, and it's cosine of 180 degrees. Why is it 180 degrees? Because the area vector is pointing to the left. Remember, it points outside the cube, and the electric field is pointing to the right. And so this here is negative, so we know it's negative E L squared. For this case here, what's the flux to the right side of the cube? Well, what's the flux to the right side of the cube? Well, I'll give you a second to think about it, but the area is the same, the electric field is the same, it's just the angle between the area and the electric field. So in this case, it's going to be positive, right? Because the angle between the area vector and the electric field is 0. How about the top face of this cube? So just to help you along, here's the area vector for the top face of this cube. Remember, the area vector is perpendicular to the surface. So think about that one real quick. Roll that one around in your noggin. Well, it's going to be 0. The angle between the area and the electric field is 90 degrees. So cosine of 90 is 0. And also, if you look at this, right, the electric field line actually does not go through the surface. It just skims along the top of the surface. What's the flux through the entire surface? Well, let's go one at a time. The top is 0, which means by symmetry the bottom will be 0, the front will be 0, the back of the cube, the one that's hidden by all the other ones, will be 0. This left side we saw is minus EL squared, the right side is plus EL squared, so our total answer, if you add them all together, is going to be 0. Here's another one for you to think about. The net flux through this cylinder here. I'll let you think about that one. This should say and it ends up being 0 just by symmetry. Through the cylinder surface, you notice that everywhere the area vector is perpendicular to the cylinder surface on the outside. The front, the area vector is pointing to the right. Sorry, the right side, the area vector is pointing that way. The left side, the area vector is pointing that way. So the flux through this side will cancel out the flux through that side. So that's a basic introduction to flux. I will provide some more for you soon.